Linear mappings are one of the most important topics in linear algebra. You may also know that matrices are a pretty relevant topic too. In this video you will learn the connection between linear mappings and matrices. You can represent every linear mapping uniquely as a matrix. We call this representation the matrix representation of a linear mapping with respect to some basis. The idea behind this is similar to the coordinate representation of vectors with respect to a basis, but more difficult. So make sure to understand the coordinate or basis representation of vectors before you watch this video. I have a video about the coordinate representation of vectors here on my channel. I will link it here at this point. Okay, before we start, I want to motivate this topic a little bit. I want to show you why the matrix representation of linear mappings is extremely helpful. So let's assume you have a linear mapping phi between two vector spaces V and W over a field K. The dimension of V is equal to m and the dimension of W is equal to n. That phi here does not need to be a matrix. It can be anything. Let's assume now that you want to find all these small v in the space capital V so that phi of small v is equal to 0. If the mapping phi was a matrix, you could now use, for example, the Gaussian algorithm to find these small v. But we don't know if phi is a matrix. As I said before, it can be any linear mapping between v and w. So we don't have any good algorithms to solve that problem here. The idea is now to represent the mapping phi as a n times m matrix, which we denote like that, square bracket of phi. Now we try to find every x in the set Km so that this matrix here, square bracket of phi times x, is equal to 0. We can use, for example, the Gaussian elimination approach to find these x here. In the end, we need to associate each of these x element of Km, which we have found by using the Gaussian elimination approach, with a unique vector small v in the space capital V. These x element of Km will be the coordinates of these vectors small v in the set capital V. These vectors small v then fulfill that phi of v is equal to 0. So we have solved our original problem. Okay, now I will show you how you can calculate the matrix representation of a linear function. Let V be a vector space of dimension m over a field K, and let W be a vector space over a field K of dimension n. Let B is equal to B1 to Bm be a basis of the space V, and let C is equal to C1 to Cn be a basis of the space W. Let phi be a linear mapping from V to W. You have to do the following thing to calculate the matrix representation of phi with respect to B and C. You have to write phi B1 as a linear combination of the basis vectors in the basis C. So you write phi B1 as S11 times C1 plus S21 times C2 plus and so on plus Sn1 times Cn. That means you have to find these coefficients S11 to Sn1 in the field K. Then you do the same for phi b2. So you want to write phi b2 as a linear combination of these basis vectors C1 to Cn. So you write phi e2 as S12 times C1 plus S22 times C2 plus and so on plus Sn2 times Cn. And you want to find these coefficients S12 to Sn2 in the field K. You have to repeat this until you reach phi bm. So phi bm has to be such a linear combination too. So you want to write phi bm as a linear combination of C1 to Cn. So phi bm is equal to S1m times C1 plus S2m times C2 plus so on plus Snm times Cn. And you are interested to find these coefficients S1m to Snm. When you are finished with all that work, you can write down the matrix representation of phi with respect to B and C. That matrix is a n times m matrix with entries in the field K. For the first column of that matrix, you take a look at these coefficients here. And then you write them in the first column of the matrix the following way. So here you have S11, that here is S21, and this here is Sn1. For the second column, you have to take a look at these coefficients here. So S12 has to be there, S22 is here, and Sn2 has to be there. You continue this process until you get to column m. In the last column, you write these coefficients here. So here is S1m, that here is S2m, and so on until Snm. As I said before, the result is a n times m matrix with entries in the field K. This matrix is called the matrix representation of phi with respect to the bases B and C. It's denoted like that: square bracket phi from the basis B to the basis C. Let's take a look at an example now. We have given the following linear function phi from R3 to R2. Phi of x, y, z is equal to x plus 2y plus z and minus x plus 2z. We have also given a basis B of R3, which looks like that. So this here is the first basis vector, this here the second, and that here the third basis vector. And we have given a basis C of R2, which looks like that. So this here is the first basis vector, and that here the second basis vector. We want to find the matrix representation of phi with respect to the bases B and C. So first of all, we have to calculate phi b1, phi b2, and phi b3. So let's start with phi b1. So b1 is that vector here. When inserting this here there, we get the following. When we solve this, we get the following vector in R2, 6 and 7. We do the same thing for B2. So phi B2, and B2 is that vector here. So we get this here, and when inserting this here, there, we get the following, and when solving this here, we get the following vector in R2, 0 and 3. And for phi B3, B3 is this vector here, so we get that here, and when inserting this here, there, we get the following, and by solving this, we get the following vector in R2, 10 and 2. Now you have to write these three vectors here as a linear combination of the basis vectors in the basis C, so C1 and C2. Okay, let's start with phi B1. So phi B1, which is equal to 6 and 7, has to be a linear combination of the basis vectors C1 and C2. You want to find these two coefficients S11 and S21. You can rewrite this here by using a matrix and get that here. Now you want to solve this linear equation system here. We will solve it directly. So from the first line here, we get that S11 is equal to 6. When inserting S11 in the second line, we get the following, this here. From this here, we can find S21. So S21 is equal to minus 5 divided by 3. So now we have found these two coefficients here. We have to do the same thing for phi B2, which is equal to 0 and 3. So we have to write phi B2 as a linear combination of the basis vectors C1 and C2. We are interested to find these two coefficients S12 and S22. We can rewrite this by using a matrix, and then we get the following linear equation system. We solve this system directly. So from the first line, we get that S12 is equal to 0. So S12 is equal to 0. When inserting this in the second line, we get that S22 is equal to 1. So now we have found these two coefficients here and there. We have to do this one more time for phi B3, which is equal to 10 and 2. So we write phi B3 as a linear combination of the basis vectors C1 and C2. We want to find the coefficients S13 and S23. So we rewrite this by using a matrix, and then we have to solve the following linear equation system. So we solve this directly again. From the first line, we get that S13 has to be equal to 10. When inserting this in the second line, we get the following. So this here. From that we can find S23. So when solving this here, we get that S23 is equal to minus 6. So now we have found these two coefficients here. Now you can write down the matrix representation of phi. You just have to fill in these coefficients here correctly. So the matrix representation of phi with respect to the basis B and C is the following. So here we have 6. Here we have minus 5 divided by 3. The second column has as a first entry 0, which is that here. The second entry is 1, which is that here. And for the last column, we get for the first entry 10, which is that here. And for the second entry, minus 6. So that here is the matrix representation of phi with respect to the bases B and C. I want to note one thing. In this case, you can solve these three equation systems simultaneously. So here we have the three equation systems. And you want to solve these systems simultaneously. So you use the following extended matrix. So here we have that matrix here. And here on the right we have phi b1, so this vector here, phi b2, that vector here, and phi b3, this vector here. Now we have to transform this matrix here on the left to the unit matrix by using elementary row transformations. This is done the following way. So first of all, we subtract 2 times the first row from the second row. So we get that here. And then we divide the second row by 3. So we divide the second row by 3. So now we get that here. So here on the left we have the unit matrix. And what we get on the right is the matrix representation of phi with respect to the bases B and C. So you can also solve this example here like that. So by solving these three equation systems simultaneously. So this is another way to solve this example. Let's take a look at another example now. We have a linear function phi from Km to Kn. It looks like that. X is mapped to A times X, and A is a n times m matrix with entries in the field K. Let Em be the standard basis of Km, and let En be the standard basis of Kn. Then the matrix representation of phi with respect to these two standard bases is the matrix A again. That follows from the fact that for k is equal to 1 to m, phi ek is equal to A times ek, which is equal to ak, and ak is the kth column of the matrix A. Now we write ak the following way. So ak is equal to a1k times e1 plus a2k times e2 plus and so on plus ank times en. These coefficients here are the entries of the column ak. So these coefficients here are the entries of ak. But because of the definition of the matrix representation, these coefficients here are also the entries of the kth column of the matrix representation of phi with respect to these standard bases here. So in the end we get that the matrix representation of phi with respect to these two standard bases here is equal to the matrix A again. So this follows from that here. Let's take a look at some properties of the matrix representation now. So we have two vector spaces V and W again over a field K. the dimension of V is equal to M and the dimension of W is equal to N. B is a basis of V and C is a basis of W. Phi is a linear function from the space V to the space W. Then the matrix representation of phi with respect to the bases B and C fulfills the following. The coordinate representation of phi of small v with respect to the basis C is equal to the matrix representation of phi from B to C times the coordinate representation of small v with respect to the basis B. This is true for all vectors small v in the space capital V. For the dimension of V is equal to the dimension of W. Phi is bijective if and only if the matrix representation of phi from B to C is invertible. If this is the case, then the inverse of the matrix representation of phi from B to C is the matrix representation of the inverse mapping of phi from C to B. Let's assume now we have another linear function psi from the space W to a space Z. Let D be a basis of the vector space Z, and Z has a finite dimension. Then the matrix representation of the composition of psi and phi, so the matrix representation of psi circle phi from the basis B to the basis D is equal to the matrix representation of psi from the basis C to D times the matrix representation of phi from the basis B to C. Furthermore, we have the following result. We can define a function f from the space of all linear functions from the space V to the space W to the space of all n times m matrices with entries in the field K the following way. F assigns to each linear mapping phi its matrix representation with respect to the bases B and C. Then this function f is an isomorphism. An isomorphism is a linear bijective function. What does that mean? So, first of all, it means that the dimension of the vector space of all linear mappings from V to W is equal to the dimension of the space of all n times m matrices with entries in the field K. The dimension of the space of all n times m matrices is equal to m times n. M is the dimension of V. N is the dimension of W. So this here is equal to the dimension of V times the dimension of W. So that means the dimension of the vector space of all linear mappings from the space V to the space W is equal to the dimension of V times the dimension of W. Secondly, it means that every linear mapping phi from the space V to the space W has exactly one matrix representation square bracket phi from B to C. It also means that for every n times m matrix A, there exists exactly one linear mapping phi from the space V to the space W so that A is equal to the matrix representation of phi from B to C. We also have that two linear mappings are the same if and only if their matrix representations with respect to the bases B and C are the same. So phi is equal to psi if and only if the matrix representation of phi is equal to the matrix representation of psi. And we have linearity. That means that the matrix representation of phi plus r times psi is equal to the matrix representation of phi plus r times the matrix representation of psi, where phi and psi are linear functions from the space V to the space W, and r is an element of the field K. At the end of this video, I want to show you how the matrix representation of linear mappings can be used to find the solution to problems in linear algebra. So we have a linear mapping phi from a space V to a space W again. Our task is now to find all small v in the space capital V so that phi of small v is equal to B, and B is an element of the space W. So phi of v is equal to B means that the coordinate vector of phi of v with respect to C has to be equal the coordinate vector of B with respect to C, where C is the basis here of W. Here on the left, we can now use one of the properties for the matrix representation of a linear mapping phi. So this here now means that the matrix representation of phi with respect to the bases B and C times the coordinate vector of V with respect to the basis B has to be equal to the coordinate vector of B with respect to the basis C. Now that here is a n times m matrix, and this coordinate vector here we will call x. The next step is to solve this here. So you want to find all x so that this here holds true. You can use, for example, the Gaussian elimination approach to find these x here, because this here is an n times m matrix. These x here are now the coordinate vectors of some vectors small v in the space capital V. That means you now have to find these small v so that x is the coordinate vector of this small v with respect to the basis B. These particular v are now the solutions to our original problem. Okay, I hope this video could show you how to calculate the matrix representation of linear mappings and why this matrix representation is helpful. If you liked this video, please consider subscribing to my channel. It would really help and motivate me to keep creating videos.